So good morning. I am very thankful to have you, Michael, with us. Thank you so much for taking the time to speak with us today. We're really looking forward to learning more about your work across quantum technologies, especially with your research in quantum computing and your applied experience in quantum sensing. So, to start us off, can you tell us a little bit about your journey into this field?
Okay, so I did my undergrad in Ghana at Kwame Nkrumah University of Science and Technology, where I was a physics major, but I specialized in electronics. And then after my undergrad, I came to Canada to do my master's at the University of Lethbridge, where I focused on quantum cosmology, which is more of theoretical physics. So within my journey in the quantum cosmology, I came across quantum computing, and then my supervisor was also much interested in quantum computing when they introduced quantum Arbiter. So due to that, I also got much interest in quantum computing, and then I decided to do much research into it. And then I realized that um, quantum computing was in line with what I was doing, and then I had a strong background for it because I already had the strong background in quantum mechanics, and then quantum computing is just applying the rules of quantum mechanics to computation. So that became much interested to me because for someone in theoretical physics where I was much focused on computer simulations and then using computing to solve physics problems, I was much interested to also see how quantum mechanics is applied to computing, and this is what led me to focus on quantum computing, and then right now I am doing much work in quantum computing.
I see. Yeah. No, that's a great entry point, especially for people who are new to the space. I know later on we're gonna talk about you said you're in doing also quantum sensing as well, correct?
Exactly.
Yeah. So, okay, for someone like me, or for those who are completely new to quantum technologies, how could you explain what quantum computing is in simple terms?
Okay,
Like
so
how, like for example, how is it different from the computers we use every day?
in simple terms, when we talk about quantum computing, for, we mostly, let me come to our daily world. We use languages to express ourselves or our feelings for another person to understand us. So when we go into into computing world, computers also have their language, and that language is in zeros and ones. So computers don't speak English like we speak English or we are speaking English currently. Computer understand only zeros and ones. So for classical computers, um, the zeros and ones are not simultaneous. They are one after the other. So when it comes to quantum computing, there is a principle in quantum mechanics which is known as superposition and then entanglement. So this superposition and then entanglement idea is what is being used in quantum computers. So then in quantum computers, the zeros and ones can be simultaneous. So instead of having zero and one, alternatively, like in quantum computers, the zeros and ones are simultaneous. So then they can you can get zeros and one at the same time. So that is how quantum computers are different from classical computers. And because zeros and ones are simultaneous in quantum computing, it makes quantum computers much faster than classical computing. So then this is in the simplest way how quantum computers are different from classical computers.
Sounds like it makes things like it really increases the efficiency. Am I
Exactly.
understanding
It
that
increases
correctly?
the efficiency, the speed. Yes. So
Hmm.
that is the basic scientific advantage of quantum computers over classical computers.
Okay, yeah, no, that
Mhm.
sounds
I
good.
see. Uh, yeah, that's very interesting. I just wanted to clarify because you know if we use quantum mechanics to do computations, it's true, right, that we can have superpositions, but that's not what you get when you measure.
Yes, that is not what you get when you measure. When you measure, you collapse the wave function, like in quantum um, mechanics. Like when you do measurement in quantum mechanics, you collapse the wave function and then you get error results. So in quantum computing, when you do the measurement, you collapse this quantumness and then you get something meaningful or something that you can present to the real world.
Yes, but that also like limits what type of algorithms you can implement or how useful the algorithms is. It's not that the classical computer is not able to follow up these computations. It's not able to reproduce the quantum state, the wave function. But also, it's not like the quantum computer is faster than the classical computer. We know like two algorithms, three, right? Is Shor's
Yes.
algorithm, amplitude estimation, Grover's algorithm, in which you can actually prove it's faster, right?
Yes,
But
in
also
short
it's like,
algorithm, yes.
yeah, yeah. And when you hear about these things, like these algorithms being mentioned, do you see any misunderstandings that are common when people talk about this?
Okay, so when I hear about people talking about these kind of algorithms, especially in quantum error corrections, um, one thing that comes in place, like what people see to be more efficient than the classical computers is that, for instance, when we're talking about error corrections in classical computing, instead of classical computing doing the error check one after the other, because of the superposition and then the entanglement um, ability of the quantum computers are able to get all the information at once and then do the sorting quickly compared to the classical component. So then that is where I see the quantum computers being um, having supremacy over speed compared to the classical computers.
Mhm.
Yeah,
Yeah, very interesting.
that clarity is really important, especially for leaders trying to understand why this matters. I kind of want to see the relevance to our world today. Why would you say, why should executives or government leaders be paying attention to quantum technologies right now?
Okay, so thank you very much for this question. So there's this paper that I published with Professor Shapiro. He is from the business background, and then I am from the science background. So we combined our ideas on how to make the quantum computers, how it should pass certain tests in business terms to see how it will be useful for business and then our real world. So basically, like there is a term in economics which is known as utility. So that has to do with the value to how something is valuable to customers or how it is valuable to our real world. So one thing that we discussed was that in my previous discussion, I spoke about how quantum computers are fast compared to classical computers. But when you're applying into real world, you don't just care about how fast is it to classical computers. There are several tests that you have to go through. So the utility test has to do with how quality is the result of quantum computers. So currently, we don't have quantum computers standing alone as quantum computers. What we have is hybrid. That is quantum computers being incorporated into classical computers. So then we compare the hybrid over the classical computers. So this hybrid is somehow like, if from my background, there is something called semi-classical approximation of quantum mechanics. This hybrid um, is of the same spirit of semi-classical approximation of quantum mechanics. So when you talk about semi-classical approximation of quantum mechanics, that is where we see like we apply classical mechanics and then quantum mechanics together. So, for instance, we have what is known as promoting classical observables to operators. So, for instance, you have the momentum in classical mechanics, and then you can promote this momentum to a quantum operator. So then instead of just, and then this is what we use to solve real world problems, especially when we want to use quantum mechanics to solve real world problems. We mostly resolve in the semi-classical approximation of quantum mechanics, where we can have the WKB approximation, but and then this is of the same spirit of the hybrid. So the hybrid, they use the classical computers and then the quantum chip together. And then the classical computers will prepare the data and then will solve some of the problems. And the problems that it cannot solve quickly, then it send it to the QPU, that's the quantum processing unit. And then that QPU also solve the problem and then send it back to the classical computer. So users actually interact with the classical computers, whilst the classical computer interact with the quantum computers. So this is the hybrid approach that we have. But to see how these quantum computers will be beneficial to our real world, it has to pass the utility test. So the utility test has to deal with how quality the result is compared to classical computers, and also budget test. The budget test has to do with the speed. And then aside the budget test, one thing that investors also consider is the cost effectiveness. So how can we implement this without spending much money in it? So then these are some of the tests that quantum computers has to must pass before it can be ready for our world. And aside being ready for our world, we have phases that it should go through. So these phases, we have the lab phase, and then we have the prototype, and then we have, after the prototype phase, then we come to how the mission is ready to be implemented. So then a quantum computer or a hybrid computer has to undergo all these tests before it can be considered as being ready for our world. So then investors or business people do not just think about the speed, but they think about how the quality of the result is, the budget, the cost effectiveness, and then also how it can be able to satisfy consumers' needs. So these are the things that business people will look at. And then that is what we handled in the paper that I published with Professor Shapiro.
Hmm. It sounds like there are some real risks of waiting too long to engage with this space because of the time that it takes, and we know about some things. I think maybe there's some space for us to talk about it later on, but there are some impending momentous dates coming, like Q Day and things like that, that people want to stay
Hmm.
ahead of. But let's
Yeah, I
connect.
wanted,
Yes, go
sorry,
ahead.
I wanted to ask one thing. This research that you did you take a look at specific algorithms for that?
Yes, we actually did specific algorithm, like where we compared classical computing solution to the quantum simulation solution. So we tried
Mm.
with Quizquit, and then we also tried with solving the problem with ordinary computers, and then we compared the two. And then after everything, we also focused on, like, we also passing on the general test that a specific quantum computer should be able to pass before it can be ready for the real world. So we did both the algorithm part, and then we also try to put on the measures that quantum computers should undergo before, like,
Mhm.
investors should would consider it investing their money into it. So we just drew the plan that everybody who is doing a research in quantum computers should follow, so that if they
Mhm.
want to make it available for the whole world to use, they don't just focus on speed, but they have to focus on what investors and then business people will look for. So we've done it. We did the two.
Yeah, exactly. Because there's like a couple of problems, right, with each algorithm. Like amplitude estimation, you need to solve first state preparation, which is still an open problem. Source
Exactly.
algorithm requires way too many qubits, right? We are
Exactly.
like decades away from that. Grover's algorithm is also very deep, so coherence times will just blow up. Okay,
Exactly.
so you take all of this into account, I see.
Exactly.
Very interesting.
Well, let's connect this to the work that you're doing. You're currently working with QuantaSense, which
Yes, I'm
focus,
currently working with QuantaSense.
yeah, and the focus is the quantum sensing. Can you explain what quantum sensing is and how it differs from quantum computing?
Okay, so I am not so quantum sense. The main idea is to go into quantum sensing, but currently, what I am doing at quantum sense is I am doing what is known as a QUILIPA. So QUILIPA has to do with the quantum limited amplifier.
Okay.
So when you talk about amplifier is just a device that amplify that enhance signal. So when you have a signal, an amplifier can enhance this signal without adding noise to it. So what we are doing currently is to see how when we apply quantum like when we apply this idea of like superconductors, when we build amplifier using superconductors, how that it will reduce noise when it is doing amplification compared to classical amplifiers. So I am doing the theoretical design of the superconductors and then how these superconductors should be built. So then basically I am working on the amplification side of the company.
Okay.
Mhm.
Um, there tends to be a lot of attention on the quantum computing and less awareness of quantum sensing. Why do you think that is?
Okay. The awareness on quantum computing and then quantum sensing.
Yeah.
Okay, so quantum computing is still in its early phase,
Hmm.
and then we are currently seeing how it can be applicable to every field. So, for instance, with the quantum sensing, the quanta sense currently, what they are trying to see is how that we can apply quantum computing to sensing, especially with temperature sensing and then other sensing, and then see how that would be effective compared to these classical sensors that we have. So then the reason why there are not much awareness in it is anytime there is a breakthrough, there will be an awareness. So right now, because it is in the early phase, researchers are still working on to bring breakthrough into how we can apply quantum computing to various fields. So whenever there is a breakthrough, it will create that awareness in which area that we have the breakthrough in.
Are there what kind of industries are already using that type of technology or exploring this technology today?
Okay, so for instance, with the quantum limited amplifier, we want to apply to drones where
Oh,
it can help with especially where and then they're also pushing it further um like I was a bit restricted by the company when I spoke with them because
mhm.
of how sensitive it is
Of
because
course.
they want to work with the they want to work with the government on it. So then they told me to not go much into yeah. So they want to apply it to
That's
the
exciting
military and
though. That's
yeah,
exciting though to know that there are these areas where this type of technology is really, really important. And again, hence why it's important for leaders in government to be
exactly.
aware of this type of technology by all means. Let me see. I think Catania has mentioned to us that you are preparing to begin your PhD yet. Concordia University with
Exactly.
quantum computing this fall.
Exactly.
Um, how does this compare? Like, what kind of problems are you exploring, or how do you see your research evolving? What's exciting you about this research this fall?
Okay, so my research with Professor Shapiro has really shaped my mind on how to approach quantum computing research. I don't have to just think about doing the work scientifically, but after doing it scientifically, how I should push it further to see how it can be applicable to the real world. So, for instance, what I'm going to do in Concordia University is on spherical harmonics, and then this is an application to quantum chemistry. So, diverting a bit into quantum chemistry. So basically what they are doing is that with their quantum chemistry, like this spherical harmonics, like it provides solution to the orbit of the electrons around the nucleus. And then basically currently what they have is that they have Cartesian grid to solve these orbits of the electrons around the nucleus. But when you think about the Bohr model, for instance, you know that the orbit of the nucleus is round. So if it is round, just applying Cartesian coordinates will be a bit tedious. So we are trying to implement spherical coordinates that is incorporating spherical harmonics to solve the orbit of the nucleus for computational use. And then this could be also applicable to make quantum chemistry more efficient, especially in solving the motion of the electrons around the nucleus. So then this is one of the things that I am going to deal with to develop the algorithm to solve the orbit of the electrons around the nucleus using spherical harmonics at the background. So then that is basically what I'll be doing. And then I'm also thinking about how I can push this research further on applying it to industry, especially quantum chemistry is mostly used in drug deliveries and then mostly also used in battery. So I've been thinking about how I can push it further into these areas of application. So that is one thing that I've been thinking about.
Mhm. I see. And when you say you look at spherical harmonics, is that you prepare a specific type of ansatz to do some VQE algorithm to approximate the ground state, something like that?
Exactly.
I see, yeah.
Exactly.
And have you thought about the problem of because usually the Hamiltonians for this type of molecule they're very long. So what you do is you get the Hamiltonian of the molecule, then you apply Jordan-Wigner to transform it into the qubit basis, and then you have a lot of terms. So that means that you need
Exactly.
to run a lot of circuits,
A lot of
right?
exactly.
So what
Exactly.
what
So these are some of the problems that I'll be tackling. So then
mhm,
um so that is why that is these are some of the problems that I'll be tackling to build the algorithm for it. So basically currently we have the
mhm.
VQE and then the VQ LS, and then all these things to solve the Hamiltonian for the ground state. So then basically like I'm yet to think about how I can build the algorithm to which will be efficient in the field of the quantum chemistry. So that is in the basic direction that I'll be going.
Yes, because once you like figure out like how many terms you have to evaluate, there's this problem like the click problem, right?
Yes,
Like how many terms of the Hamiltonian can you measure at the same time? But
exactly.
given the terms of the Hamiltonian, solving that problem to see how many circuits you need to run is
Yes.
NP hard,
Yes,
right?
that is that is something that I'll be encountering. So yeah, I'm aware
Yes.
of that. So yeah,
Okay.
I've been thinking about it, how to get all these things done, like when I start in fall 20 this September.
Okay, do let me know if you solve that problem. I will be
Sure,
really interested. Yes.
sure.
That sounds so fascinating. So, Marco, how does this compare? Like, where is your background? How does your field overlap with what Michael's interested in, or are you in a totally
It's
different?
uh, so I'm more on like AI or optimization and quantum computing, but like theoretical side.
Mm-hmm.
But all my group like they also do things on chemistry, materials, things like that. So I'm aware of the potential and the limitations of all these things. So yeah, like I heard my colleagues complain a lot about this specific problem, the
Mm-hmm.
click problem. So yeah, we like as a whole will be really interested in this type of
It's
problems.
fascinating for someone like me because when you hear the word quantum, you just think it's one kind of discipline. But then, with some of the work or talking with other people, like here I'm hearing about chemistry and materials, and then another time somebody is talking about how it relates to business and portfolios. Like it just security. It's, for me as a person, I just like even when we're just talking about chemistry right now, yeah, I don't, and then then you mentioned medicine. It's just like so many different, it's fascinating for me. And like it makes me wonder, like right now, as an English teacher, we're just thinking about things like Chat GPT and AI, right? And I know that they're not the same, but I can feel this surge of this technology that's coming up. And looking ahead now, Michael, like where do you see quantum technologies in the next 5 to 10 years? I've been hearing and I'm learning a lot more about what this Q day is, but which areas will you see an impact, in this world? What milestones should someone like me be watching out for?
Okay, so I think quantum computing or quantum technology will be impacting every aspect of our lives, especially like everything that because currently like it is being incorporated into everything.
Mhm.
So it will be useful for every aspect of our lives. And then that is the reason why I am very much eager to embark on the journey into quantum computing and then also with what I have been doing because little did I know that quantum computing will be applicable to drones and then amplification and then amplifiers and then now it is being used it is being applied there and it is also um applied in material science and then medicine just as you said so
Mhm.
it is being applicable everywhere. So then that's the reason why I'm so much eager to enter into this field, not just as a researcher, but also to contribute to this area in quantum computing and use it to solve real world problems. So some of the problems that I would love to solve is problems in medicine where quantum computing could be useful, and then problems also in material science and then battery production. So then these are some of the areas that I have already targeted to use quantum computing to solve.
So you are with University of Lethbridge. You're going to Concordia. I think Marco Sherbrooke University. I'm in the high school in the education realm here in Alberta. Well, what do you see or what impact is Canada having? How can governments support the growth of quantum innovation here in Canada, or where are we sitting in the world in terms of impact when it comes to quantum technology as Canadians?
Okay, so from what I know, especially working within Quantum City at University of Calgary, realize that the government has put much money to support quantum computing research, especially with Quantum Alberta, where it is linked to University of Alberta, University of Calgary, and the University of Lethbridge. So this research that the government is spending money on, I've seen a lot of progress going on because it is out of this investment that the government did. That is what birthed Quanta Science, where I'm currently working. And then um, there are other companies that are also coming in, like with the hunger to solve problems using quantum computing. So I see that this is a good step that the government of Canada has really made to advance quantum, or to advance and then invest in quantum computing, and then it's going to have a great impact on Canadians and then technology that we have in Canada as a whole. So this is a good initiative that the government is doing, especially investing in quantum computing.
That's good to
Mhm.
know.
Yeah. Can I
Yeah.
add something to this? Yeah, I agree with you that like quantum sensing is an amazing technology. It's already working, but something that most people don't know is like the quantum sensor gives you much more information, but you need to filter it. So the quantum sensor doesn't work alone. It needs to be working with an AI who's going to filter all of these things. So it's actually this is like a combination. It's quantum technology and AI. They need to come together. Another thing is that for quantum computing, I agree with you that there's potential about it, but I don't see how it can actually be applied. Like even like if we build a quantum computer tomorrow, we still have problems to solve, right? Like and on the algorithmic side, things like state preparation, which is used like for any problem in chemistry, in finance, in banking, all of these things, like we think they might work like this because we are able to take one of their problems and map it to the computer. But that doesn't mean it is efficient or that it's costly, right? As you said,
Yes,
like on your first paper. So I think it's interesting also like trying to play a devil's advocate when you see news on quantum computing, like all these things, because a lot of people think that we'll be able to use quantum computers like as soon as they're available to solve problems, right? But however, it is very interesting for military applications, government applications, right? Because that's something we know that the Shor's algorithm is going to work, and
exactly.
there's a lot of research on the algorithmics of Shor's algorithm. They're reducing the number of qubits, they're reducing the depth of the circuits, and quantum computers are going to get there soon. So from that side, governmentally, like it's needed to do research on these things.
Exactly. So that is why I said that I really like the fact that the government is investing into the
Yeah,
research aspect. Yes, where the research is being conducted to help us solve these problems.
Mhm.
yeah, they better be because any other government is doing the same thing.
Well, it's really nice to hear how you are kept motivated to stay in such a complex and evolving field, and I see the impact that it will have for us. And it's nice to it's comforting for someone like me to hear that that's something that our country is aware of and investing in. What advice do you give to students, potential students, lovers in education interested in quantum technology? Like if there's someone who is just starting into, post-secondary and looking for a field, has some interest in say this quantum science, like what advice would you give to them?
Okay, so the advice I'll give is that students should take their math serious, especially linear algebra, because on a fundamental level, quantum computing is just linear algebra. So students should take their math serious so that when they get into it, they will be able to enjoy what is being taught, especially with eigenvalues, eigenvectors, and those things. And then like if you don't have the math background, you struggle to be able to be in it. So then that's one advice that I'll give them. They should take their math serious, especially with linear algebra. And
Mhm.
then um I would say that it is a growing field. So if you have a vision of um, imparting the world, especially where the world is heading to. So that's what Marco said, that quantum computers and then AI. So then I believe this is what will take the world in the next
Direction.
30 or 40 years to come.
Yeah.
So if you want to be part of revolutionizing our technology and then the world, then I think quantum computing is one of the field that you should get into because this is what we are using to revolutionize our technology and then revolutionize our industry like medicine and everything. So this is one thing that I believe like if you want to be part of it, you should get into, especially with quantum computing and then AI.
Hmm. That's very fascinating to know. Yeah, I do suppose math would be a very basic fundamental interest for a
Yes,
PhD
math is the
student.
basic fundamental thing, especially with linear algebra.
Yeah, no, that's very
Yeah, yeah.
good to
So,
know.
I always
Um,
tell students when I talk to them, like on at the level of college, and I tell them, look, people say quantum is weird because it is math,
mhm.
right? Like if you know
Yes.
the math, you're good with it.
Yes, yeah, that's the basic language. Well, Michael, you have the floor for any last words that anything, something current that you are really fascinated with or working on or promote anything that you have. What would you like to
Can
share?
you give me the floor? I really
Yes,
need to ask because I'm very curious. Please
yes.
tell me about your research on quantum cosmology.
okay, so my research on quantum cosmology was the use of the Wheeler-DeWitt equation, like was applicable to I was using the Wheeler-DeWitt equation to see whether there was thermalization in the early universe because this universe that we are living in started with a Big Bang. And then during the time of the Big Bang, the universe was very small to the extent that it was of the order of the Planck length that the laws of quantum mechanics could be applicable to the universe as a whole until it started expanding to this bigger universe that we have where classical laws dominate. So we wanted to understand the origin of thermalization using quantum cosmology or quantum. So quantum cosmology has to do with the application of quantum computing and application of quantum mechanics to the universe as a whole. So we wanted to understand how, when we apply the laws of quantum mechanics to the early universe, you'll be able to understand how thermalization came about, and then how this thermalization, because help to see whether this thermalization will be able to help us to understand the mystery of dark matter and then dark energy. Because when you talk about thermalization in cosmology, it has, especially in the early universe, when the universe was very small, it was hot and dense. So as it started cooling, that is when these particles and then different matter came into being. So this is a thermalization process when you think about it using the concept of thermodynamics. So we want to know how this thermalization also resulted in the creation of dark matter and then dark energy. And then because we don't understand the mystery of dark matter and then dark energy. So then we believe that when we try to understand thermalization at the early universe, we will be able to solve some of the mysteries in dark matter and then dark energy. So
So
then that
did you do that looking at the microwave background radiation, or did you use any other tools?
Okay, so basically what we did was we just resorted purely on the math to see whether the math in quantum cosmology to see whether there will be thermalization in the early universe. So for instance, the Wheeler-DeWitt equation that I have at the background, you have the Hamiltonian acting on the wave function, and then it gives zero. So this is the Wheeler-DeWitt equation or the Schrodinger equation in quantum cosmology. So
Hmm.
for instance, this wave function is what carries information about the universe that we have. So when you solve this wave function, and then we try to understand for different kind of for matter dominated and then radiation dominated, and then when you solve this wave function, and then we also try to apply the concept of accelerating observer and then static observer, like Unruh effect. For
Hmm.
instance, when you take this Unruh effect idea, when you have a vacuum, a stationary observer will see nothing in a vacuum. But when this stationary observer is moving within the vacuum, this stationary observer sees a thermal bath at the background in the vacuum. So although it's a vacuum, but for different observers, they see different things. So for a static observer, he will see nothing. But for an accelerated observer, he will see a thermal bath at the background. So to be able to link the two, we have what is known as Bogolubov transformation. So this Bogolubov transformation is what we use to link the two.
Mm.
So what we did was that we solve the wave function for a static observer, and then we also solve it for an accelerated observer. And after solving it for the accelerated observer, we use the Bogolubov transformation to link the two. And if the Bogolubov transformation was unity, then it means that the system is not thermalized, then that means that there is no thermalization. But as we solve for the wave function of the universe for static and then accelerated observer, and
Uh,
then we use Bogolubov transformation to compare the two, we realize that the system was a mixed state. And then applying the principle of statistical physics, where you see that the system is a mixed state. That is when psi is not equal to psi squared, then it means that the system is a mixed state. So then this idea of the mixed state suggested that this wave function that we have for the universe as a whole, um, when you solve for both accelerated and then when you solve for a static observer, and then you use the Bogolubov transformation to link the two, we see that the solution that we get from the Bogolubov transformation suggested that psi is not equal to psi squared. So that means that there is a mixed state, and then that hinted that there is a thermalization in the process. So then that is basically what I did for the masters.
okay, one last question. How
Okay.
do you solve for the wave function of the universe?
Or how we solve for the wave function of the universe.
Yes.
Okay, so basically, like this is a normal quantum mechanics problem because, for instance, this Wheeler-DeWitt equation that we have here, if it's something really strange because we know that the Hamiltonian generates time translation. So that is why for the normal Schrodinger equation, we see that the Hamiltonian is a generator of time translation. But for something really weird to our understanding, when this Hamiltonian acts on the wave function of the universe, it is equal to zero. It doesn't generate time translation. So then that created the idea that we have, that created the problem that we have in quantum cosmology, which is the time problem. So where how time even emerged in quantum computing. So then they use what is known as relational time instead of the normal classical time, because when the wave function, the Hamiltonian, which is a generator of time translation, act on the wave function, it gives zero instead of generating time.
Mm.
So
Is that because you have a degeneracy on the zero state?
the
On the zero
degeneracy,
vector?
oh, not really. So this is something that um was the problem in the when Wheeler and then DeWitt solved for the Hamiltonian for the universe as a whole. So then we didn't really understand what was really going on in the system because it seems that it's static. And then this is not problem because this is not problem to the problem from this has to do with the fact that one of the problem when we are incorporating general relativity and quantum mechanics is that in general relativity we know that time is just one aspect of space. So time and space are together. But in quantum mechanics, time and space are distinct, like the normal Newtonian concept. So
Mhm.
then, because we want to incorporate general relativity, which has a different concept for time to quantum mechanics, where time and then space are distinct, it also resulted in we having this kind of problem for time. So then
Mhm.
that's what made people to start questioning what is time in quantum cosmology, because it seems that the Hamiltonian, which is supposed to generate time translation, is giving us zero, or which means that the universe should be static or something like that. So then this is some of the problem
Mhm.
that we encountered. So
Yeah, yeah.
to when you have this wave function, you can use the WKB approximation for solving the wave function in quantum mechanics to solve the wave function in the quantum cosmology. So basically what I did was to use the WKB approximation to solve the wave function for the universe. So then that is what I use.
Hmm. I see. I see. Yeah, that's also one of the applications of quantum computing that I'm really looking forward to. I don't know if you heard about this experiment that putting two quantum computers, one on Earth, one in space. So you
Yes,
have two quantum systems on different curvatures of space-time. Man,
exactly.
when we can build that, we will know things. Hey, thank you very much. I'm extremely interested in what you're doing. You need to send me your papers. I'm gonna shut
Sure.
up right now because I could be talking about this for hours.
Sure.
Thank
I'll be
you.
very glad to collaborate with you to publish a
Yes,
paper.
please.
Yeah, I'll reach out to you.
It's so fascinating to hear like the two of you. Like I said, having a room with great minds sharing this, it's very fascinating for me. Now, from my perspective now, for a person like me, where would you say we are right now in terms of real world impact? Not that the work that you're doing isn't impacting the world, but closer to someone like me where, at one time, this type of technology wasn't even on our body several years ago. I have six children of my own, and my eldest is 26 and my youngest is 14. And the type of technology that my children have been exposed to from my eldest to my youngest, have we seen such a rapid change, right? Even just parenting with that type of technology. So, where would you say we are right now in terms of real world impact to family like mine? Are we closer than expected or still a ways off? Is there a lot of work to do? It sounds like just hearing you two talk amongst yourself, like it sounds like it's just right around the corner. So, what is your opinion of that?
Oh, okay. So I would say technology is advancing. So for instance, if you take cars, in the olden days, they used to use horse for their transportation. And
Yes.
then we evolved to the usage of cars and then the usage of flight. So
Hmm.
technology is advancing. So what quantum computing is doing and then where we are right now, I think we've passed the stage of, for instance, when quantum mechanics started, it was just a theory. And then we didn't know how we can apply this theory to the universe because when it started from the philosophical point of view, like you have a wave function and then this wave function collapse. And then like when you're observing, like you are seeing something else. And when you are not observing, you are seeing something else. It was kind of weird how we can apply this concept in real life. But now, as I can say, we've now been able to reach where engineers are also now taking over um, the ideas in quantum. computing, and now we are beginning to apply them in various fields. So what I would say is that we we are getting somewhere. Like we are really, really, really getting somewhere. Like it's not just a theory or not just a research, but currently it is being studied to how we can apply it in different field, and then we are getting there. We are getting there. Not that we are almost there, but we are getting there because it's compared to how when it started, that it was just a theory and then we didn't know how to apply it. Now we are getting there, and then we are getting to know the use of quantum computers. So I would say in the next 20 years to 30 years, like we will see quantum, our quantum computers everywhere.
That's that is really exciting to hear about. Um, You have the floor for any last words that you want to promote, where your passions, both in the lab and not, yeah, tell, any last words from yourself?
Okay, so I would like to work in the industry where I will apply my knowledge in the research field to solve problems related to quantum computing, and then how they are being applied in the industry. So I would say that currently, like open like when I start my PhD, I'm open for internships in IBMs and then also in quantum computing company, any startup that would want to, that's interested in my background and then would want to work with me, open for any internship opportunities and then any opportunity in the industry to also apply my knowledge that I have gathered so far in quantum computing to solve any problem they have. So this is something that I'm really, really hoping to get.
Thank you again, Michael. This has been incredibly insightful. We're really excited to share your work and perspective with the broader audience. I'm excited to see any collaboration between you and Marco.
Yes,
And
I'll be
yeah,
expecting that.
yeah. And thank you for taking the time to speak with us, especially from us here at Cuba, from the Cubo perspective. We really appreciate your time.
Okay. I also appreciate and then thank you, Luna, and also thank you, Marco, for this opportunity to also speak with you and then exchange knowledge. I'll reach out to you so that we
Yeah.
can publish paper together.
For sure.
Yes, I have my daughter. She's second year at the undergraduate at the University of Alberta. She's in chemistry. She's doing a lot of research in chemistry. I said, you have to find, so I got excited when you said chemistry today. So I want to find a way to connect you to this because it sounds like this is the direction to go.
Yeah,
So again,
exactly.
yeah, to
Tell her
both of,
about quantum chemistry and then computational chemistry.
yeah, yeah. But for
You can
the,
tell her to apply for an internship here at the Algo Lab at the
yeah,
Instituto Quantic.
yeah.
Yeah, yeah.
I have the highest respect for both of you. Thank you again. And yeah, we will be in touch. I can't wait to get to share this information that you've shared with us today.
Yes.
Thank you.
Have a good
Thank you,
rest.
Michael.
Okay,
See you.
thank
Thank
you.
you.